Welcome. In the last lecture, we have seen initial value problem of homogeneous and inhomogeneous type. So this is inhomogeneous initial value problem. Okay. Here I have d psi dt is equal to a psi t plus f of t, where f is some integrable function. Okay, f is in L1, and initial point is data is a point in the Banach space. Small x is in capital X. Okay, for this equation, it may not always admit a classical solution. Nevertheless, what we have seen in the last lecture that one can, of course, define one function this fashion, ttx plus 0 to t capital T of t minus s fs ds, where this capital T is the C0 semigroup generated by the operator A. So then this function as a function of t is called mild solution. Okay, so even if a strong solution does not exist, the solution of this classical solution does not exist, if capital A generates the C0 semigroup, then one can write down a mild solution of this equation. We have also given the motivation behind the reason why should we call these as a mild solution. Okay, so today we are going to see that we are going to see under what condition on this f one can assure existence of a classical solution. We know that if f is 0, then of course just for a small x in the domain of A, one can get a classical solution. Correct? So here, if instead of 0, if f is non-zero, okay, so for that, what type of things do you need? Okay, so here from this expression of a mild solution, one can get some idea. Okay, so let us see what idea can I get. Okay, although that apparent idea what we may get needs justification and rigorous proof. So first intuition is that I would like to have sufficient regularity of this mild solution. Okay, like if psi is a classical solution of this equation, then psi should be differentiable. Okay, so for that, if x I choose from the domain of the operator A, then ttx is indeed differentiable. Okay, also we would like to have a psi to be meaningful. Now, if x is from domain of A, then ttx is also in the domain of A, then that this at least this part would be in the domain of A. Okay, so I can put x in the domain of A, then we can get the required smoothness at least for this term, but we have another term also. Okay, for this term we know that this is just an integration. So if we do not go into the details what is written inside the integrand, we know that this is some L1 function. Okay, so if you have L1 function and you integrate, so it's locally integrable. Okay, so locally integrable function integrate 0 to t some compact set, and then with time you change, then that is a continuous function. Imagine that this has no t dependence inside. Okay, imagine that I have integrand which is without t dependence, and then if it is just an L1 function and you integrate from 0 to t as a function t, the whole thing should be continuous. Okay, now in addition to that, if I don't have, if we have just instead of just integrable function, we have a continuous integrable function. Okay, if this is there is no t dependence, just this is a function of s and it is continuous, then after integrating 0 to t, what we get is differentiable in t. So from that, one can ask a very valid question that if I choose my function f, this this additional data, to be continuous, can we expect that the whole integration would be differentiable? If we can get this, that this is differentiable, then psi would be differentiable for every x in the domain of A, and then this makes sense. Okay, and when this makes sense, we can make sense of this part also, and then one can get that, okay, this psi should be classical solution of iIVP. Okay, however, we would see with some example that that is not the case, that just mere continuity of f does not give differentiability of this term. Why? Because after all, I have another term which also depends on t. Okay, so at present, therefore, it is vague. It is not clear that what condition we need to put here for on f so that this equation would have a classical solution. So at present, we are looking for a set of sufficient conditions on this on f. Okay. Nevertheless, one can put a direct condition, I mean entangle with a and f together, that this whole integration is this thing is differentiable. Okay, if you put this way, then that would immediately give that this equation would have a classical solution. Okay, so this is the thing which we are going to discuss today. I mean, the set of alternative sufficient conditions on these functions, etc., would also get some other little stronger condition f, for which would not need to put a condition which is entangled with a and f, correct? Because if I say that this integration is differentiable, then that puts a condition on both a and f together. Okay, so we are going to see examples and some theorems results today which would clarify this aspect. Okay, so this part we have already discussed earlier. So, existence of classical solution we are going to discuss today. So, as I have discussed just now, that additional assumption of continuity of f does not also ensure existence of a classical solution with initial point x in domain of A. Okay, I mean, I have not given any example yet, but I would surely give an example, okay, towards the end of this topic. So where I would exactly provide you one particular f, okay, and particular choice of x. Okay, so where f would be continuous, but the equation would not have a classical solution. Okay, so this example I have taken from the book of Apazi. Okay. Okay, so if this is not a sufficient condition, just continuity of f is not sufficient condition, what should be that? So conditions that guarantee the existence of classical solution to iIVP is given below. So first, we assume that a condition A, that A be the infinitesimal generator of a C0 semigroup TT. Okay, so first condition on A, so this is standard condition that it generates a C0 semigroup. Okay, so this condition is common in the earlier lecture also. For homogeneous case also we have had this assumption on A. Now second condition, that f is in L1, so it is integrable and it is continuous on this 0 to t. Okay, this is time interval t. Okay, so we are looking at, I mean, finite horizon time point. Okay, so then what we do is that we define Vt, that integration 0 to t, capital T of t minus s fs ds. So this whole thing as a function of t that I call as v of t, and we assume that one of the following holds. Okay, one of the following holds for Vt. I mean, that we have already started discussing, that V is continuously differentiable. V is in C1 of the on this open interval 0 to capital T. This is one. Otherwise, we also, another alternative assumption is that V of t is in the domain of A, domain of the generator A, for each and every t, and after applying A on V, so AVT, okay, AV, that is that is continuous function, okay, it's continuous function from this open interval 0 to t to x. So assume that A has this standard assumption, and on F continuity, and in addition to that, we assume that this integration is either continuously differentiable or this integration is in the domain of A. Okay, so additional condition. So under this, we have a conclusion. Then the initial value problem, okay, which is stated in the earlier slide, has a classical solution psi on the interval 0 to t for each x in the domain of A. Okay, we cannot expect that we can assure classical solution for any arbitrary initial point, because that is even not true for homogeneous case. Okay, so we can at most expect x belongs to the domain of A for that. Okay. Okay, good. So if the iIVP has a solution psi on interval 0 to t for some x in domain of A, okay, then the reverse is also true. What? That then V satisfies both 1 and 2. Okay. So here this says that this is like a necessary sufficient condition. Okay, given that A generates a C0 semigroup, then this is an if and only if condition, because if V satisfies either of these condition, then iIVP has a classical solution. On the other hand, if iIVP has a classical solution, then this V satisfies both these conditions. Okay. Okay, so this is this theorem is serving its purpose. It is really giving necessary sufficient conditions for existence of classical solution of iIVP. However, we are not fully satisfied with this statement, because after all, here this condition on V is condition on both A and F, because a condition on I mean, it is entangled, correct? There is semigroup and F both appears here. So semigroup property which depends on A, that also appears here. So we are going to see some other statements, other results also, which do not put condition on V, but only condition on F. But those are a little stronger. So those are not if and only if conditions. Those are sufficient conditions. Okay. So before going to another statement, we just see the sketch of the proof. We are not going to prove this part from here to here. We are going to prove from here to here. Okay. So here we from the definition we derive that V of t is equal to psi t minus ttx. Why? So let me show this here. So here Vt is equal to this integration, and here when we have seen the formula of variation of constants, then psi is equal to ttx plus this integration that we call now V of t. So psi of t is equal to ttx plus V of t, or in other words, that V of t is equal to psi t minus ttx, correct? So we can get here V of t is equal to psi of t minus ttx from the definition of Vt. Okay, so now we would like to use either of property 1 or 2 to obtain that psi is differentiable. Okay, psi is differentiable, and not only that, psi satisfies that iIVP. Okay, so what we do is that here we take the semi-group T of H. H is a small positive real number. T of H minus identity divided by H. Okay, V of T. So we do this. Why do we do this? Because that as H tends to 0, this would give me AV, correct? The generator we are going to get. Okay, so TH minus I VT. And now recall the definition of VT, that is integration 0 to T, capital T of T minus SFS ds. Now, if I operate T of H on this integral, the T of H that because since it is bound linear operator, and then the inside the integrand also we have L1 functions, so we can put this T of H inside the integration, and then inside the integration we already have capital T of T minus S, and then this capital T of H together. Using the semigroup property, we are going to get capital T of H plus T minus S. Okay. See here that if I have here, this is V. If I have capital T of H on this, so capital T of H goes inside, and then capital T of H composition, capital T of T minus S together would give me capital T of T plus H minus S here. Okay, integration 0 to T. So here I have T plus H minus S, but I have small t here. However, I can add and subtract the integration T to T plus H of this term to get here 0 to T plus H, this term to T plus H minus S, and then minus small t to T plus H, if capital T of T plus H minus S f of S ds. Okay, so one can write down that way. So we do that. Here capital T of H VT, so this operation, from that I would get 0 to T plus H, this integration of this, which would give me exactly V of T plus H, but I have to also keep in mind the subtraction, that is T to T plus H, capital T of T plus H minus S FSDS. Okay, so this I because I have added there, so I have to subtract also. So that would give me, so this operation T of H on VT operation gives me VT plus H minus this thing, and then minus identity VT is giving minus VT. Okay, so this left hand side is written this way. Now here this looks pretty simple. This is basically the finite difference of VT. So as I mean, if V is continuous differentiable, then this exists. Okay, or the second property, if V is in the domain of A, then also this limit exists. Okay, so either of these limits would exist. So here, on the other hand, if F is continuous, okay, so if F is continuous, then we know that this limit exists. And what is that limit? That as H tends to 0, this would be actually the value of the integrand by putting this T plus H. I mean, it should be 0 there. I will need to put 0 instead of H, and then this integration S T to T plus H. So instead of S, I have to put small t here. Correct? So this the limit of this thing would be the value of just the integrand, where H is replaced by 0 and S, the running variable, is replaced by t. Okay, so if F is continuous, so this part 1 over H T to T plus H, capital T of T plus H minus S FSDS, so that converges to capital T of, so H is 0, S is T, so T minus T, capital T of T minus T, F of T. So this is capital T of 0, that is identity map. So that of Ft is Ft itself. So this whole part becomes f of t. Okay. So now, since this limit exists and either of these two limits exist from the assumption, so the earlier assumption here, either of these is true, correct? So either of these would give me either of these two terms exist, okay, the limit exists. So then what we get, the other should also exist, because this limit exists, so this limit exists, so then this also should exist, or this exists and this exists, that would imply that this should also exist, okay, because left hand side limit exists, that means right hand side limit also should exist. So we would get that this limit exists on both the sides. We take the limit, and then what we get from the left hand side is the generator A. So this is AVT here, and this is V prime T here, and then this whole thing converges to FT, so minus sign is there, so minus F of T. So after taking limit, we get this as either of 1 or 2, 1 and 2 is true. Next, what we do is that we go back to this equation, V of t is equal to psi t minus ttx. Since here we have already obtained that this thing, so here we take the derivative V prime, that is equal to psi prime. I can't take derivative because if either of that 1 or 2 exists, so then both exist, so the both limit exists, we have seen here. So V prime is equal to psi prime minus the derivative of ttx, okay, tt prime x. So that we write down here by taking derivative, psi prime is equal to V prime plus ttx prime. Okay, so now here we have an expression for V prime already we have obtained here that we are going to use now. Okay, so this is equal to V prime is AV plus FT, because this FT would come here. So V prime is equal to AV plus F. So AV plus F, okay, V prime is written as AV plus F. And then ttx prime, so derivative of ttx is ATTX, correct? So that we have seen in the beginning of the topic of semigroup theory. So this I am going to get ATTX. Now here I see the operator A, here also operator A arises. So we can take common A from these two terms. So A, if we take common, so I would get inside the bracket V of t plus ttx, okay, and then plus f of t. Now V of t plus ttx is a known quantity. What look at here? So Vt is equal to psi t minus ttx, or in other words, psi t is equal to Vt plus ttx. So this Vt plus ttx is nothing but psi t. Okay, so I write down that is equal to A psi plus f. So what did I get? I got psi prime is equal to A psi plus f. That is the inhomogeneous initial value problem. D psi dt is equal to A psi plus f. Let us go back again to the initial value problem to see. So d psi dt is equal to A psi plus f. Okay. Okay, so next we come to that example. So as I have discussed that only continuity of f is insufficient to ensure existence of a classical solution given the initial data is coming from the domain of A. So this is illustrated by this example. As I have discussed that this example appears here. So we start by showing that the continuity of f in general is not sufficient to ensure the existence of solution, that means strong classical solution of the iIVP, okay, inhomogeneous initial value problem for x in the domain of A. Indeed, let A be the inferenceable generator of a C0 semigroup TT. Okay, so assume that is there, and let small x is in capital X be such that TTX is not in the domain of A. Okay, we consider one particular x such that TTX is not in the domain of A. Okay, for any t greater or equals to 0, let f of s, okay, the data we choose cleverly here, that f of s is defined as ts of x. See, this x is not the initial data, okay, it's just an arbitrary small x, okay, such that ttx is not in the domain of A. Okay, so if x is taken from the domain of A, then TTX must always be in the domain of A, but otherwise it need not be true, correct? So if you choose TTX, if you choose x not from A and ensure that it is chosen such that TTX is not in the domain of A, okay, so that we consider that type of x to construct one f, okay, in this fashion, f of s is equal to ts of x. So here, since capital T is a C0 semi-group, we would get continuity of f from here, from the definition. So fs is continuous. Now consider the initial value problem. Du dt is equal to aut plus ttx. Okay, so here f of t is replaced by ttx. Okay, and initial data is just 0. Okay, as I told, x is not the initial data, it is taken just to construct one f function, and here initial data is taken as just a 0. Okay, so 0 is of course in the domain of A, correct? Because th minus I by ah of 0, that is 0. Okay, so that limit exists, etc. So 0 is always in the domain of A. So we claim that this example equation star, okay, has no solution. No, it has no classical solution. So although that u of 0 is this 0 is in the domain of A. Okay, and here see, I mean, the initial data is in the domain of A, the function f is also continuous, but still we are going to show that it cannot have a classical solution. So let us see the details. It is not very long. So indeed, the mild solution of star is obtained using the variations of constants. The formula of variation of constants says that u of t, the solution u of t, should be equals to tt of 0. Tt of 0 is 0, and then that does not appear. Then plus integration 0 to t, capital T of t minus s t, and then fs ds. Fs here is ttx, correct? So if t is ttx, so fs is tsx. So I should write tsx ds here from the formula. Okay, but this is a semigroup, the same semigroup, correct? So we can operate, and what we get is the tt. Okay, so ttx ds. So then t minus s ts gives tt. So this inside, this integrand becomes independent of the s variable. So this integration would be small t times capital Tt of x. Okay, so this is ut. Okay, so the mild solution of this equation is nothing but small t of ttx, small t times ttx. Okay, so now question is that, can it be a classical solution? The answer is no. Why? Because this, to become a classical solution, this thing necessarily should be in the domain of A. However, ttx is not in the domain of A, so this is not in the domain of A. Okay, so but ttx is not differentiable. So since it's not domain of A, so this is also not differentiable. Okay, we have seen that, okay, if x is ttx is not in the domain of A, so then this is not differentiable. So this is clearly not the not a classical solution of iIVP. Okay, so this is the proof of the statement what we were saying, and this also therefore clarifies our concerns and emphasizes that why do we really need a very good condition, some sufficient condition for which we required that either of these things to be true. Okay, so we really required something more than just continuity of f. Okay, fine. So next we go to another theorem which gives another set of sufficient condition for existence of classical solution to the iIVP. So a simpler sufficient condition, let A be the infinitesimal generator of a C0 semigroup TT if f is itself continuously differentiable function. Okay, C1 0t to x, right? F is the Banach space valued function, x valued function on the time interval. So here if f itself is C1, then iIVP has a classical solution on this interval for all x in the domain of A. Okay, so sketch of the proof. So I'm just giving a sketch of the proof, not the details one. So what do we need to show? That if since I'm using differentiability, continuous differentiability of f, we need to show that the mild solution is sufficiently smooth and it solves classically. So here we look at v of t. So here we are going to apply the earlier theorem. So if we just show that v of t satisfies either of the conditions 1 or 2, then we are done. So v of t is integration 0 to t capital T of t minus s fs ds. So here we now substitute the variable t minus s as u, and then t minus s is u, so s is t minus u. So it would become capital T of u, f of t minus u, and then when s is 0, u would be t, and when s is t, u would be 0, and ds is minus of du. Okay, so from there, since minus sign is there, t tends 0, so we can change the limit these things and remove the minus sign. We get 0 to t ts ft minus s ds. Okay, so v of t can be written this way. And now here we see that t dependence appears here and here. Okay, and f is c1. Now we use Leibniz rule for differentiation under the integral sign. So if f is in C1 using differentiation under the sign of integral, we would be able to show this whole thing is also differentiable. Okay, whole thing that is v. And then we would be able to use the earlier theorem. However, we see the details that how that Leibniz rule apply here. So the derivative of v prime t is equal to, so now first we consider this t variable. So here differentiation of this would be just the integrand where h should be replaced by t. So we get capital T of t, f of t minus t, that is 0, f of 0, plus, now we keep this integrand, this fixed, and we take differentiation inside. So integration 0 to t, capital T of s, and f t minus s is there, so f prime of t minus s ds. Okay, so this is the application of Leibniz rule. So v prime is this. And then this thing I can rewrite using exactly the same way, similar manner, by changing the substitution variables. We can write down that as 0 to t integration capital T of t minus s f prime s ds. Okay, so f prime exists, etc. So this is the way we can justify that, and here why should it exist? Because f is in C1 0 to t closed. Okay, so the derivative is continuous on the closed interval, so derivative is bounded. Since it is bounded, so this integration makes sense. This will be finite. So v prime, okay, so v prime exists. Okay, so now we can actually apply the earlier theorem, correct? Earlier theorem where v prime, exists. So v is C1, and that would lead us that existence of classical solution to the iIVP. Okay, so this is a sufficient condition for existence of iIVP. Okay, next we see another very interesting theorem which talks about approximation of mild solution by classical solution of approximated equation. So remember, we have iIVP, and in iIVP the given initial data x or the inhomogeneous part small f r may not be very good, so x need not be in the domain of A, or f need not be differentiable, etc. However, if one has a sequence xn in the domain of A which converges to x, okay, that means if x is in the closure of domain of A, and if one has a sequence fn which are C1 and converges to f in some sense, then the sequence of initial value problem which we can construct using this fn or xn, so they would have classical solution, and those classical solutions are good approximation of the actual mild solution of the actual initial value problem. So this is the thing which we need to discuss now. Let f is L1 function. If phi is the mild solution to iIVP on the interval 0 to capital T with small x in capital X. See, we have not assumed any strong condition on either f or x. Okay, so we can only assure existence of a mild solution if that A is generator of a C0 semicolon. So then we get a mild solution. Okay, so then consider sequence fn in C1 and xn belongs to D of A. If exists, then we consider, okay, such that xn converges to x in the norm, okay, the Banach space norm, and fn converges to f in L1 norm. Okay, then for every t prime which is less than capital T, okay, if we take phi n is what? Phi n is where phi n solves iIVP with f replaced by fn, x replaced by xn. Okay, so this phi n, which is classical solution of approximated equation, and phi is the mild solution of the actual equation, then this solution of approximated equation is a good approximation of the mild solution in this sense, because the sup norm sense, correct? They converge, uniformly. So phi n t minus phi x, this norm over x, supremum 0 to t prime, this whole thing converges to 0. For any t prime which is less than capital T, we consider and we get it. Okay.